Hello everyone, my name is Cindy Amanyere, and today I'm going to take you through our project. It's an EEG based stress detection using machine learning, and it's reinforced contrastive knowledge distillation for mental stress EEG analysis. So, like we all know, stress is a very significant concern in both healthcare and workplaces. Like it can lead to diverse conditions. So we've come up with a model, a machine. Our work is majorly around coming up with a machine learning model that can detect stress by reading your brain by reading your signals for you from your brain. Yeah. So we have our problem statement, which is our application. So we have application domain specific problem where mental stress negatively impacts health, performance, and well-being. Then we also have EEG signal providing an objective measure, then requiring complex analysis. So these are the technical computational challenges. We have high dimensionality of EEG data. As we all know, this is typically high dimensional, meaning it contains a large number of features or variables, and this can make analysis computationally intensive and can lead to issues like overfitting, where a model learns the noise in the training data rather than the underlying patterns. Then we also have noise and artifacts in EEG signals. So, like muscle movements and external interference can obscure stress-related signals. Like we all know, EEG signals are prone to various types of noise and artifacts, and this can distort the brain activity signals. Then we also have imbalanced data classes where more non-stress samples than just stress samples can lead to biased predictions, like especially those related to disease diagnosis. Like the data can often be imbalanced with much larger number of samples from one class. Yeah. So now our key techniques we're going to use, we have knowledge distillation. This is a technique where a smaller, simpler model is trained to mimic the behavior of a larger, more complex model. And it transfers knowledge. Like the whole concept of knowledge distillation is transfer of knowledge from complex models to simpler ones, improving efficiency without sacrificing accuracy. Then we have reinforcement learning, whereby an agent learns to make decisions by interacting with an environment, and this continuously refines stress classification by adapting to new data and optimizing decision making. Then we have sparse learning, which involves techniques that promote sparsity in the parameters or representations of a model. Yeah, like it selects the most relevant EEG features and this helps to reduce computational complexity while maintaining performance. Then we have contrastive learning. Contrastive learning is a self-supervised learning technique where a model learns to distinguish between similar and dissimilar pairs of data, and this helps to enhance the model's ability. So we have electroencephalography, which is EEG in short. Then this is a medical imaging technique that measures electrical activity in the brain using electrodes placed in the scalp. It captures brain activity through non-invasive sensors, providing real-time neural data for stress detection. Like we are designing a headset that can be worn on your head and detects the brain signals to deduce the stress levels. Yeah. Then supervised learning, which is a type of machine learning where a model is trained on labeled data. Yeah. So we're going to look at the data selection. So our data sets, Our dataset collection is collected using an EMOTIV EEG 5-channel sensor kit, and these tasks include complex mathematical problem solving, whereby we were able to get to 22 participants. We have trial mental challenge tests, 24 participants, troop color word test, 24 participants as well. Then horror video stimulation, 22 participants. Then relaxing music as well. And this data was collected to investigate. This data was collected to investigate neural responses to stress. So this next page, it shows a data sample of different faces and how they, like this face shows someone, the first face shows a stressed person. Then there are some faces that are showing some people crying. So this is an example of our data set. This is an image example. Then, so we have EEG, the EEG signal processing workflow. So we have noise filtering. Noise filtering basically is a part of a pre-processing that involves removing unwanted noise and artifacts from the EEG data. And this enhances the quality of the signals. Then you have wavelet transformation for feature extraction. Then this is a mathematical technique used to decompose EEG signals into different frequency components. Then we have normalization for model training, whereby it involves the scaling of the EEG data to a standard range, such as 0, 1, or -1, 1, like these ranges. Then, like, we have feature selection, which involves identifying the most relevant features from the EEG data that contribute to a classification task. And this also helps in reducing the dimensionality of the data and improving the performance of the classifiers. Then we have model training. This basically deals with using selected features to train a machine learning model, whereby the CNNs with transfer learning are used for stress pattern detection. Then we have classification, whereby this is the final step where the trained model is used to classify EEG data to predefined categories. And this optimizes the stress state identification. So moving forward, we're going to look at the applications of EEG-based stress detection. So healthcare, like this model can be employed in psychiatric health centers to detect mental health cases. Yeah, and like it can also be used in hospitals, let me say for stress diagnosis, or you know how stress kind of contributes to high blood pressure levels. So this can also be used as one of the diagnosis methods. So workplace safety, whereby you can implement a real-time stress tracking system for high-risk professions to enhance safety and provide employee well-being programs to promote overall mental health. Like if this model can be employed in workplaces, like at work you come, like if you're having a bad day, your boss can like call you and test your head to see if you're stressed or if you need a break or if you need a leave. Yeah, then it's education, like detecting cognitive stress in students to better understand their learning challenges and develop effective strategies for improved academic performance. Like this helps to streamline the performance. Like if the teachers are able to detect the stress levels by this model. Yeah, thank you so much. Let me invite my colleague to take you through the graphs and the visualizations of our EDA code. Thank you.
Good evening and good afternoon. My name is Kaunde Audrey, and I'm going to be taking you through the EDA code. So for this part, the first snippet, we see this section of band powers. And in the band powers, we have the alpha, which is for relaxed state, mental state. Then the beta is used the beta is for when you're alert. And then the theta is for sleep. while gamma it's tied to high cognitive functioning of the brain. So that's basically what the band powers plots, the alpha, beta, theta. Yeah, that's what it plots. Then we have the skewness and kurtosis. So this shows the shape and distribution of the data in the data set. Then we also go to the PCA. This is potential component analysis, which is used for, this plots in form of clusters to differentiate between stressed states and non-stressed states. So we proceed to the amplitude distribution. This shows the power of the signals, and it's measured in volts. Yeah, it shows the power of the signals of the EEG signals. And then we proceed to the box plot, which also almost does the same thing. Yeah, the strength of the signals, the EEG signals. Then we move on to the heat map. It shows a relationship between the different signal patterns. That's what an EEG correlation matrix does. So when we proceed to the next page, we have the beta band pass, which is used in EEG signal processing to remove noise. And when we get that relevant information of the brain activity that's needed. So these are the alpha, beta, theta, and gamma waves that I was talking about. Yeah. So we proceed to the next graph, which is the EEG signal amplitude distribution. As I said, it shows the strength of the signal. As you can see, it goes up to almost 8. Then when we proceed to the next, we have the pair plot. So the pair plot just shows us, it's like a variation of the different EEG data. So the pair plot shows the relationships between the variables in the data set. As you can see, we have very many graphs here. Yeah, to tell the relationship between the variables in the data set. The EEG signal amplitude box plot is like, it measures the frequency of the signal, but this time in box plot format. While for the EEG time series or timestamp, this measures the amplitude variations over time for the timestamp, while the violin plot measures the signal in different conditions, under different conditions. So when we proceed to the next, we're going to look at the skewness and kurtosis. Like I said before, this determines the shape and distribution of the data in the data set. While this shows the EEG signals, the brain activity of the person, but in EEG signal format. Then we have the correlation matrix, which shows the relationship between the variables, and it comes up with a correlation where you see the red ones in a line. That's the correlation. So we have the spectrogram, which shows how the different frequency components vary over time. Like you can see here, the small lines. So that's what shows the variations over time. So we proceed to the next. So this shows the band powers, and the band powers are the strengths of those different waves. The waves used to detect stress, which are the delta, theta, alpha, beta, and gamma. So we can see that gamma is the highest. That means there was high cognitive function in this person's brain activity. So we have the raw EEG signals. These are basically straight from what the model got directly without any kind of editing. And the PCA like I said before, it shows clustering. So here it clusters to show the different stress states, highly clustered and sparsely clustered. Well, it will, the highly clustered represents something else, and the sparsely clustered also represents another thing, maybe stress or relaxation, the different things. Then we go to the next. So in conclusion, we focus on improving our model interpretability for better understanding by healthcare professionals and expanding the model for real-time EEG stress monitoring using wearable devices such as headphones or maybe a watch, making it a for continuous stress detection in workplaces, healthcare places, schools, and all that. Yeah. So we use in this model we use reinforcement learning, contrastive learning, knowledge distillation. Yeah, and all these improve the real-time performance of the model. Thank you for listening to me and have a good day.